All right, that seems to be pretty stable, so we can get started now. My name is Mark Coleman. I'm the CNCF Marketing Chairperson. We're joined today by Nick Chase from Mirantis, who's going to be telling us about machine learning and AI in the data center, not dental center, and how it will affect you. Now, we've had an unprecedented number of signups, and that means there's also a lot more people in the call. None of you are able to speak, but what you can do if you have questions is put them in either the Q&A or the chat. And I'll try to find opportune moments to interrupt Nick and ask him those questions. But I can tell you ahead of time that we're not going to be able to get to all of them. So I apologize for that. Nick will probably give you his social media details or something during the call. And you could perhaps follow up with him later. I do, though, encourage you to ask questions during the webinar as opposed to just at the end. Nick, are you ready?
I am as ready as I'm going to be.
Well, that's excellent. Take it away.
All right. Well, thank you very much, Mark. Good morning, everybody. Welcome to today's webinar. I kind of like the whole dental center thing, though, but we'll move on. Before we do go anywhere, I want to tell you a little bit about me. If you've ever been at any of my webinars, you know that I tend to whip right on by this slide because, let's face it, you're here for the content. You're not here for me. But this time it's important that you know something about me, and that's that while I am an experienced programmer and I do a ton of technical content, and I'm even the author of a course called Machine Learning for Mere Mortals, what I am not is a PhD in math. Now, I'm not saying this because I want you to think I'm an idiot or anything, but I know that until I started getting into machine learning, I thought it was this mystical math thing that was incomprehensible to people who weren't working in some basement laboratory somewhere. I was completely intimidated at the idea of getting a computer to do what I thought were these magical things. Then I started looking into it and I found something out. First off, if you are one of those math PhDs who does all this fabulous research and discovers new algorithms and creates toolkits like TensorFlow and scikit-learn to make this stuff possible, God bless you. We couldn't do it without you. Please don't kill me for what I'm about to say next. Here's what I found out. Actually doing machine learning, that is understanding the basics and getting the computer to figure something out, is something you can pretty much do with high school algebra, if that. And that is because we have these toolkits that let us mere mortals do machine learning, which is about to open up a whole new world of what we can do. And that's what we're going to talk about today. So if you work in IT or you're a developer or you're just interested in what machine learning can do and how it does it and what that's going to mean for the data center going forward, this webinar is for you. If you don't know anything about machine learning, we're going to give you the basics. If you do know about machine learning, but you want to know how it'll apply in the data center, this webinar is for you. If you know about both of them, I don't know why you're here, but I'm glad you're here. Please stick around. We'd love to hear your perspective towards the end. So, of course, while I'm going to give you the basics, we cannot possibly cover all of machine learning in an hour. So I've talked Manning Publications into giving away free access to my upcoming video course, Machine Learning for Mere Mortals, to everyone who's here live today. If you're catching the replay, I'm going to try and do something for you too, but if you're here live, you will get access to the Manning Early Access Program, which means that you get to see the draft videos as they're completed, so please go easy on me if there's still some glitches. So you can hit that link here and fill it out. We'll also put the link back up at the end. All right, so a quick look at what we're going to talk about here. We'll start out with a quick introduction to machine learning itself and the different types that are out there, and then we'll move on to the various issues that face the data center and how machine learning and AI techniques can help solve them. Then I'm going to show you how easy it is to actually do this stuff by working a simple example with you using TensorFlow and a little bit of Python. You are not going to believe how straightforward this is, I promise you. Finally, we'll tie it all together with a look at how to get started, and we'll go to Q&A. All right, so let's start out by making sure that we're all on the same page and look at just what we're talking about when we say machine learning. All right, so here we have the obligatory definition. Machine learning is the study of enabling a computer to perform in situations it may not have seen before. So what does that actually mean? Let's look at it this way. If you go to your browser and you type in kubernetes.io, the browser knows exactly what to do. It goes to the Kubernetes website. That's not machine learning. If you just type in Kubernetes, that's probably not really machine learning either, because Google knows exactly what you're searching for because you typed it in. On the other hand, if you open up Siri or Google Assistant or Alexa on your phone and say, what is Kubernetes? That's a whole other story. First, whichever assistant it is has to translate the sounds you've made into specific words, and then it has to interpret what you meant by those words. Now, of course, your phone doesn't have labeled sound files of you speaking every word in the world, so it's going to have to interpret what you said by comparing it to sound files that it does recognize, or probably more specifically, features of those files. The point is that the system learns to do things that it hasn't explicitly been trained to do by extrapolating from knowledge that it already has. Now, while we may think of AI and machine learning as something really new, in fact, it's been around for a fairly long time. And these days, it's probably pretty difficult to get through even a day without being affected by it in some way or another. Some of the more common places it's used would be in analytics to help interpret data, advertising, of course, to help target people who are most likely to be receptive to your message, bots to make them sound more like humans, general pattern recognition, such as identifying specific types of customers, or even identifying where there's a particular need for a new product. Natural language processing for things like, to hear your balance, say balance, or to determine what people are talking about online, and of course, search. Now, more recently, we've seen it in image recognition. So, excuse me, you can go to Google Images and type in pretty much anything, and you'll get a pretty good selection based on a text request, which is pretty cool. To a lesser extent, this applies to video as well, though of course this isn't quite as advanced yet. Machine learning is also showing up in places like cybersecurity. IBM's Watson has been pushing hard in the medical space, using machine learning to help predict outcomes to try to help doctors make better decisions. And then, of course, there's self-driving cars, which is a machine learning task that probably would have seemed unthinkable even a few years ago, the Jetsons notwithstanding. Now, before I move on here, I want to make something clear. I have a friend who referred to this as the Oprah slide. You get AI, and you get AI, and you get AI. Everybody gets AI. I don't want to give the impression here that you need to do everything at once. I'm just showing you some of the places that it is being used out there. Going forward, you are better off just kind of picking one little piece to start with. All right, but getting back to what I was saying. These are not just weird little companies you've never heard of working on this stuff. If you go to Indeed.com and you look up machine learning jobs, you can see the companies that are looking for people who understand this stuff. The day I was putting this deck together, these were the top companies. Some of them, you expect, like Amazon and Apple and Google and Facebook and Oracle and IBM, and even the staffing companies aren't a big surprise. But look at this. Number 2 and number 3 on this list are JP Morgan Chase and Goldman Sachs. These are financial companies. I mean, I haven't talked to them, but judging from their job listings, they're looking for people who can help them make better business decisions and who can help them use machine learning to enhance their security situation. Interestingly, it also looks a little like they've added machine learning as a keyword for a lot of their IT-related jobs that don't immediately look like ML jobs. So it just goes to show you how important this is becoming and how important it is to learn it now so that you don't fall behind. And it's not just established companies. I have the Product Hunt plugin, and every single day there's at least one AI or ML related startup featured. Every single day. You can go and look in the AI category, and there are literally hundreds of them there. And why is that? Certainly not because there's been an explosion in math PhDs with too much time on their hands. Now, the difference is that there are now easy-to-use toolkits like TensorFlow and scikit-learn that make it possible for anybody who's got a little bit of programming skill to put together real AI applications. So that's why it's taking off. And because the people most likely to be interested are the most technical, the data center is the natural place for this to be showing up. So before we move on, I do want to clear up one little bit of potential confusion. So far, we've been using the terms artificial intelligence and machine learning interchangeably, and we'll kind of do that throughout the webinar, but it's not 100% accurate. First, let me say that even the experts haven't really decided how they feel about this, but generally the way that I look at it is that artificial intelligence is the overall field of trying to make a computer do things we previously thought only a human could do. But that it also includes things like, complicated decision trees that aren't necessarily machine learning, which is using algorithms and potentially training to teach the computer to handle situations it hasn't seen before, as I was saying. And inside of machine learning is another term you probably have heard, deep learning, which is a type of machine learning that involves neural networks, which is another term you've probably heard. Okay, so what does all of this have to do with cloud native computing? Well, quite a lot, actually, if you really want to achieve the full potential of what's possible. So let's take a quick look at what cloud computing really means. First, you have environments that are inherently dynamic. Cloud native applications need to be built in such a way that various resources can disappear and be replaced at any time. And in an environment like that, humans can't be expected to constantly be on top of everything that's happening, especially once you get beyond a certain size. Everything has to happen very quickly. If a cluster goes down, it needs to be replaced immediately, not when somebody gets a call and logs in and looks around and decides what to do, which is why we have continuous automation. Problems have to be corrected without human intervention, and systems need to be optimized even as they're changing. And all of this requires observability. You have to know what's going on in order for either a person or the system to make good decisions. And I may be making it sound like there's not enough information, but that's absolutely the opposite. In most cases, there's too much information. And that's another reason why we need machine learning and other AI techniques to interpret it. And of course, all this needs to be done efficiently in terms of performance and resource usage and cost, and that also requires powerful analysis. Now, am I saying that none of this can be done without machine learning? Absolutely not. You could do all of this without machine learning, but without it, the computer is only as smart as we teach it to be. And as these environments get more and more complicated, that's going to have the potential to become a problem. Okay, so if you do add AI and machine learning elements to your infrastructure, what do you get? Well, you've heard of continuous delivery infrastructure where you can get continuous improvements to your software. We like to think of this as intelligent delivery infrastructure, which takes things to the next level. So let's take a quick look at what that means. Now, first off, an intelligent delivery infrastructure means that you have a defined architecture. This might be salt manifests or puppet scripts or whatever it takes, but we are definitely talking about infrastructure as code here. So that these automated routines know what they're trying to achieve, or at the very least, what they're starting out with. It also gives you accountability and auditability. You also get an architecture that's flexible. You or your automation can change it at any time, but it's controllable. You always know what you have and where it is. Now that observability becomes intelligent oversight. You can have systems that watch over what's going on and make sure that issues don't become problems, provide optimization and healing operations as appropriate, and so on. And finally, with all of that in one place, it's much easier for you to get appropriate security because AI routines can catch outliers that point to attacks before they cause damage. So that's a very quick version and a very quick vision of what we could get by incorporating machine learning into our infrastructures. Now let's get a better idea of how machine learning works, and then we can look at how it can actually do those things. So let's start by talking about some of the different kinds of machine learning that are out there. So probably the simplest to understand is supervised learning, which is when you train the computer using data that's already labeled so that it knows how to recognize similar data that it hasn't seen yet. Typically, there are two types of problems here. There are regression problems where you're trying to determine the value of something, like the price of a stock on a given day in the future, or classification problems where you're trying to determine what something is, like, is this a cancer cell or not? Some examples of supervised learning include image recognition, speech recognition, medical outcome prediction, spam filtering, stock market and crypto pricing is another one. You'll also notice that all of these are situations where we feed the system lots and lots and lots of training data so that it knows, say, what a picture of a bus looks like, and then it can recognize other buses. But this training can be extremely extensive and frankly quite a hassle. So there are also a couple of other kinds of machine learning. Now, unsupervised learning is where we just give the computer the data and let it figure out the patterns without us. Now, obviously, if we just gave an untrained routine a pile of photos, it's not going to be able to figure out what a penguin looks like. But it might give you back groupings of birds versus fish, or it might give you back black animals versus white animals versus multicolored animals. The point here is that it may make unexpected connections, which is good, because sometimes there are situations where we might not even know what it is that we're looking for. Some examples of unsupervised learning include clustering, where the system tries to figure out what various bits of data have in common, such as trying to group customers into categories so you can sell or advertise to them effectively, or chemical compounds, so you might be looking for a new drug or figuring out what's going on in a new environment. Unsupervised learning can also be used to find things that just don't belong. This kind of anomaly detection is good for finding security breaches or for predicting hardware or software failures by finding patterns that just don't look right. You can also use it to separate various signals. Think of it like trying to separate the lyrics from the music in a sound file, or different conversations at a party. Only now think of that in terms of, say, the signal that's coming from an industrial sensor. Another type of machine learning that's a bit more complicated is reinforcement learning, where you basically give the computer an objective and it tries different things until it figures out the best way to achieve that objective. And actually, when you come right down to it, that's how we humans learn to do something. We keep trying until we figure out how to do it right. So reinforcement learning is where, rather than training the routine using labeled data, it trains itself via trial and error. So some examples are, like I said, just about anything that humans do, or self-driving cars. Obviously, that's a simple goal. Don't crash into anything. So they let the car run various scenarios and it figures out, if I'm drifting towards a light pole, I should probably change direction. Or if a car's stopping in front of me, I should stop too. One place that's really useful is strategy development, such as gaming. You're probably used to hearing about computers beating humans at chess, and now there's a new program that can beat the best Go players in the world, which is supposedly much, much harder. And gaming is really great for reinforcement learning because you can basically have the system play another version of itself to figure out what works and what doesn't. Though I should point out that, at least for the moment, humans do still win at StarCraft. It's not just gaming. There are more practical uses for reinforcement learning, such as scheduling. Classically, they refer to this as the traveling salesman problem, where you need to figure out the best route for the salesman to travel to minimize his expenses and maximize his or her profits. But you can also think of this in terms of network latency, since we're trying to talk specifically about the data center. Okay, so now before we go on to talk about this data center specifically, are there any questions that we need to hit right now?
Hello. Yes, probably. Yes. We got a whole bunch. So let's have a look from not the top. Let's go with the bottom. Someone asked about URLs. Then someone else mentioned that. Oh, okay. What is the difference between different kinds of optimizers like AdaGrad and so on?
Oh goodness. Yeah. So I'll tell you what, let's hold off on that one until we get into talking about gradient descent, which we will in a little while, because that's going to be more relevant at that time. I'd have to explain it to answer the question. So we'll wait till we get there.
So we're just going to wait a little bit with that one.
Let's just do that.
There was one comment that was sort of interesting, which Christian said, maybe mention that, yes, it is possible without machine learning, but in many cases, the sheer volume of data makes that very expensive. Perhaps you could talk to that.
Absolutely correct. And I was going to mention that a little bit later. That's we have so much data coming in from like the Internet of Things and all of these metrics and everything like that. We are, as a storage expert friend of mine said, absolutely drowning in this data if we don't figure out ways to eliminate things that we do not need. So yes, absolutely, absolutely crucial. We don't need to store everything. And as I was going to say later, it scares the heck out of me because I am somewhat of a data hoarder, and I hate to let anything go because I'm sure that the minute I do, I'm going to need it. But we have to, and that's someplace where AI can really, AI and machine learning can really shine. So, all right, I'll tell you what. Let's grab the rest. Let's kind of move on, and then we'll grab more in a little while. How's that sound?
Sounds great.
All right. So let's talk about some of the difficulties in running an efficient data center and how machine learning and AI techniques can help us there. Now, remember, I'm not saying jump in and do all of these things from the start. I'm just trying to show you that there are opportunities to improve things with AI right under your nose if you want to go that way. All right, so starting at the beginning of the process, let's talk about configuration. Now, self-service is supposed to be an advantage, and it is for administrators because they don't have to have the burden of providing resources for everyone who needs them, but it pushes that burden down to the developer who may not be familiar with what's available or specifically how to take best advantage of it. Listen, I've been a developer for years, and I know I don't want me making decisions about the best way to set up a data center. And the situation is even worse now that we have microservices, because once you've got the system itself set up, there are still so many theoretical choices for developers. There are tons of opportunities to shoot yourself in the foot and have problems. And of course, with dynamic environments, we have lots of opportunity for configuration drift. This is either going to get worse with immutable architecture because it's all baked into instances that are going to break when things change, or it's going to get better because people know that it's baked into instances that are going to break when things change and they're going to take care of it. Personally, I think it's going to be worse unless we get better processes in place. And really, you can think of a lot of these things like playing a game of broken telephone. You remember the game where you whisper something to someone and they whisper it to someone else, and by the end of the line, you don't recognize what comes out. It's funny when it's a game. It's not so funny when your entire infrastructure is in metaphorical flames. So how do we add intelligence to this process? Well, for one thing, a machine learning routine can look at previous deployments and potentially figure out, well, this is similar to this app, which did best when it was deployed this way, so I'm going to recommend that, or even just do it. And actually, even after it's been deployed, you might use reinforcement learning to get it to retroactively improve performance or research usage. And once things are configured, you want to get that optimization right, which can be tough because in this distributed dynamic environment, there are a ton of factors to consider. And some of them are probably not even visible to the developer, much less controllable by him or her. And even if you do get a perfectly optimized environment or deployment, once things change, like a cluster goes down or there's a network slowdown somewhere, your optimization goes right out the window. So by using machine learning, we can create a setup that takes into account multiple factors and the way they all interrelate in a way that humans are going to have a hard time matching. The system can also predict future load and proactively take steps to scale up. So for example, if your company ran a Super Bowl ad, the system might take several factors into account and realize a slight increase during the commercial wasn't just a blip and scale up before a huge increase hits when the commercial's over. So, or your system might expect more people to be watching that game in Philadelphia and Boston based on patterns you picked up beforehand and redirect resources accordingly. Sometimes the optimization isn't even about performance, but it's about cost. With the rise of public cloud and a pay-as-you-go strategy, making sure you're not paying for something you don't need is really important. To give you an example, I myself recently got a bill from AWS for $156 for load balancers. I didn't even realize I had spun up when testing something the previous month. So there are way more moving pieces than most people can keep track of. And even if you do keep track of them, the prices are always changing. Fortunately, the unit prices generally are going down rather than up as all of these companies fight to get you locked into their own cloud. But the fact remains that there are often times when you are not on the most cost-effective resources, even though you were yesterday. And we can't overlook the obvious. This gets to Christian's question. With all of this data flying around, there's more every day, and we are running into these huge storage costs. There's one auto company that generates so much data on a test drive, they can't transmit it to a central location fast enough, and they have to send hard drives in a chase van. That just blows my mind. So in terms of how machine learning can help, of course, one thing that it's very good at is keeping track of all of these multiple parameters, so you can figure out if you're better off on this system or on that one based on usage in ways that maybe aren't obvious. For example, maybe computer's cheaper at provider A, but you don't use a lot of compute. You use a lot of storage and you transmit a lot of it, so you're better off at provider B. And I'm, again, not saying you couldn't code something to figure this out without machine learning, of course. I'm just saying that it lends itself to that, especially in these changing environments. And as far as the storage issue, we talked about this earlier, just keep what you need. And AI and ML can help you figure out what that is. Okay, so you've got everything configured, you've got it optimized, you're not paying more for it than you need to, but things can still break. Hardware goes down, software configurations drift, we talked about that earlier. Sometimes you have data corruption going on, and you might not even know. You might have silent data corruption caused by bad firmware or even loud noises or cosmic radiation. Silent data corruption doesn't get noticed by the operating system, and you might not find it until it's much, much too late. Remember that broken telephone analogy. This could be a huge issue before you even know it. You might need to get a head start on running out of storage or memory or other resources. So, of course, you can do auto scaling without machine learning, as we've been saying, but by adding it in, you have the ability to do more sophisticated versions of it. You can also let the system detect patterns that might indicate a disk is going to go bad in the near future, or other hardware resources are going to, issues are going to pop up. So you can move data or resources and replace that hardware before it becomes a problem. Machine learning is also good for detecting non-patterns or anomalies that indicate something isn't right, whether, again, hardware going bad, software data that's been corrupted. And of course, there are security issues, which is somewhere that machine learning is already in play. I think we're all pretty familiar with distributed denial of service attacks. Potentially even more scary is advanced persistent threats, where the attacker gets into your system ahead of time and just sits there undetected for months or even years, just stealing data and doing all kinds of untold damage. And then there's inside jobs, where somebody should have access, but they're doing things they probably shouldn't be doing, even if it's all technically allowed. So machine learning gives us the ability to do this anomaly detection to find those APTs. You might also use it to find situations where somebody's doing something that's just not right. And of course, pattern recognition can help you detect when a DDoS is headed your way, so you can take steps to prevent issues in so much as that is possible. It might also help you locate the source of the attack and block it. Obviously, that's tougher with a distributed attack like the Mirai botnet, where millions of IoT devices were taken over and used for this kind of thing. But that's the whole point. A machine learning routine might quickly figure out that that's what's happening and help you filter out that traffic. Okay, so now that we talked about some of the things that machine learning can do for you, I want to show you how easy it is to actually do this. Before I do that, though, I want to tell you a really quick story. About 15, 20 years ago, I was writing for a very large, very sophisticated company, and I won't name them for reasons that will become obvious in a minute. They invited me down to their offices in the Southwest to see a new program that they were working on. And they were trying to create software that was self-configuring, self-optimizing, self-healing, and self-protecting. Now, as I was typing this into the deck, I realized that this is pretty much what I was describing in the last section. But at the time, I kind of looked at them and said, well, if it's self-configuring, self-optimizing, self-healing, and self-protecting, how do you turn it off? Oddly enough, they were not very pleased with this question. And frighteningly, they didn't really have an answer. But the point here is that as technical people, we have a responsibility to understand what it is we are trying to unleash on the world. Fortunately, as I've been saying, it's not as tough as it sounds. So let's dive in. Okay, so in this example, we're going to try and create a Python script that uses machine learning to predict the best approximation for a set of points. In this case, it's the relationship between the length of an article and the number of shares that article got. And of course, there are any number of lines that we can draw that approximate this data, and some are going to be more accurate than others. But how can we quantify how accurate each line is? Well, what we're going to do is we're going to define the error for each line. So let's say we have just these 5 points. So if we're going to draw a line, each point would be a set distance from that line, represented by these green lines. And of course, the smaller the total distance, or the less green, the better an approximation that line is. But how do we figure out that distance? Well, this is a simple XY coordinate system. So we have, for each point, we have the Y value, and we have Y predicted, which is what the line thought Y would be for that particular X value. So the length of each of those green lines is going to be absolute value of Y minus Y predicted. We're using the absolute value because we don't want any negative distances. So the total error for this line is going to be the sum of all the individual little green lines, or the sum of the absolute value of Y minus Y predicted. But how do we know what Y predicted is? Well, that's where high school geometry comes in. You may remember that the formula for a line is Y equals mx plus b, where m is the slope of the line, or how much it's tilted, and b is the y-intercept, or how high in the graph the line sits. Now, obviously, looking at this picture, those two values, the slope of this line and where the line is, are going to determine how good of an approximation that line is. So what we want to do is we want to guess the values of m and b that are going to give us the least amount of error. Now, of course, we don't want to run our data center on just guessing, but fortunately, there's an organized way to do this. Now, let's say I told you that I was thinking of a number between 1 and 100. And if you guessed, I'd tell you if you were too high or too low. So if you're being logical, you'd probably start by guessing 50. And I tell you were too low. So you'd know it was between 51 and 100. Then you'd probably guess in the middle of that, or 75. And then I tell you that you were too low. So you'd know it was between 76 and 100. So then you'd guess in the middle of that, or 88. And I tell you we're too high. So now you know it's between 76 and 87. So you guess in the middle of that, or 82. And I tell you were right. So even though 100 is a huge range, with just 4 guesses, you got the answer. And when we run the algorithm, we'll see that the routine does pretty much the same thing, in that it can make huge gains at the beginning and then slow down. So if we were going to graph the error based on the guess, you can see here that on the left, the slope is negative because we're moving towards the right answer. And on the right, it's positive as we're moving away from the right answer. Right at the right answer, the slope of this line is 0. And that's what we're trying to find. We're trying to find the place where the slope of the error is 0 because the error is at its minimum. So if I were to vastly oversimplify this, if you know the math here, yes, I know I am vastly oversimplifying this, the error might look something like this. And we're going to try and make sure that we're always moving downhill, so to speak, so that we can get down here to the bottom. One thing to keep in mind, though, is the size of the steps we're taking. If we were taking steps that were too small, it'd take a really long time to get to the bottom. If we take steps that are too big, we could wind up missing the bottom altogether and just bounce back and forth between the two sides. So if we put all that together, we get a technique called gradient descent, which is basically an algorithm that tries to find the parameters that are going to give us that minimum error. Now, to do that, we're going to need a couple of things. Now, obviously, I don't have time to take you through all the setup and everything, but if you fill out the form for machine learning for mere mortals, I'm probably going to put together a blog post on how to get things set up, so you'll get notified about that. So the pieces are the data, of course, which in this case is just a CSV file. Python 3, TensorFlow, which is an open source machine learning library, and it's all running in this case on Ubuntu. So if we look at what we're actually going to do here, it's pretty straightforward. We'll read the data, then we'll define the model, which in this case is that y equals mx plus b. Then we'll define the error in the optimizer. Then we'll repeatedly run the optimizer until we get as close as we can to the right answer. All right, so let's go over to my Ubuntu machine, which probably is not set up in the right window, but we will. Okay, let's, okay, apparently I cannot come out of, let's do that. There we go, got it. All right. So if we go here, you ignore that stuff, like I said, we will come over here to our file. This is what I get for not proofing this section ahead of time. This is how you know it's live, folks. All right. So now I already generated this data. I generated this data myself, so I would know if we were getting the right answer. So the shares in this case are going to be 0.37 times the article length plus 12, plus or minus some random amount. So we know that the right answer is going to be, oh, come back here, no. Come back here. The right answer is going to be y equals 0.37x plus 12. So m equals 0.37 and b equals 12. So let's actually go ahead and do this. All right. So we'll start out by just importing the pieces that we need. This bit here is just to suppress some warnings, so just ignore that. And then we'll go ahead and we will load the data. Oh boy. Okay, so we're going to go ahead and load the data. There we go. We're going to set some column names so that we can refer to them by name later, and then we'll create an array pointing to that CSV file. Now we're going to start by defining the model. Okay, we'll go ahead and grab that. All right, so we're defining the model. You remember, we're looking for y equals mx plus b. So we're going to define our initial guesses for m and b. And just to show you that I haven't fixed this in any way, we're going to use random numbers. Then what we're doing is creating a single TensorFlow variable, w, which is basically an array of m and b. TensorFlow variables are special because TensorFlow knows that it can update them as it runs the optimizer to try and get closer to the right answer. Now, then for the model itself, we basically need three values. We need the article length, the shares, and the number of shares the model predicts that we're going to have. The first two are TensorFlow placeholders, which means that when we run the optimizer, we're going to feed in the data for them. And then the predicted shares is just mx plus b. So w0 times the article length plus w1. Okay, so now we need to get the error. Now before we were using the absolute value of y minus y predicted, but we're going to go ahead and use the square because it will always be positive, and also it's going to accentuate the error so we can get a really good feel for what's working. So we'll take the square of the shares minus the predicted shares, and we'll sum that up to get the total error. Now, one quick thing here, we're going to start out with some astronomically large errors, especially since we're squaring the difference. So to prevent us from getting numbers that are too big or too small for the computer to handle, we're going to scale this error by 10,000. So I've already got this in place. There are other ways around this problem, but we don't have time to talk about them at the moment. So we've got it here, and that's ready to go. All right. Now, so we scale the error. Now we can set up the optimizer itself. First, we're going to choose the step size. Now, remember, we talked about that earlier. You can experiment with different step sizes. I'm going to use 0.0025 because that's about as big as I can get without having a problem. And then we create the optimizer, which is the gradient descent optimizer. We talked about that question earlier. I will get to that later. We're giving it the step size, and we're telling it that we want to minimize the error. Just make it so you can see more here. There you go. All right, so now that we've created all these variables, we want to go ahead and define the model as this collection of variables, and we're ready to run it. Okay, so we've defined the model, and we will run it. Now remember, we specified, we're going to create a session to run all this. Okay, so we got with session. Now remember, we specified our initial variables as random numbers, so it would help if we printed them out so we know where we're starting. Okay, and now we can run the actual optimizer, and we'll do that. We'll start out by defining the data that we want. Okay, we're creating this data to use variable right here, and then we're feeding it the data that we got from our CSV file. Okay, so when all that's done, we will print out the value that we got. And then down at the bottom, I have a routine that goes ahead and prints out the graph. So let's go ahead and run that. If I can get to the right screen. Thank you. Just ignore that. All right. So that, by the way, is what happens if you don't scale the weight. Now, you can see here, we started out with our values. Oh, no, don't do this to me. Apparently, the demo gods hate me today. Just a moment. The demo gods are not with me today. Just a moment, please. Come on, buddy. There we go. Okay. So now we're running it, and it's supposed to be terrible at this point because we are supposed to have only one guess, but apparently we ran through and we did all of them. Yes, we did. Remember I said I didn't rehearse this part? There you go. So if you only ran one guess, it would be terrible. Okay, you would not get a good answer at all. So instead, what you want to do is you want to go ahead and run it multiple times. So that is what we are doing. We are actually running it through 20,000 times, as you can see. And so we've set the data. We are running the optimizer, the error, and the weight, and then we're outputting them here, but we don't need the optimizer, so that's what that underscore is. It's just a placeholder. And we're feeding it data to use. And every 1,000 iterations, we're printing it out, and we get the answer. And you notice it came to the answer really, really fast. The cost did not shrink at all. Normally when I run this, in fact, I'm going to run it again just to see. First of all, you can see we got pretty close, 0.367 plus 15. If we ran it again, come on. If we ran it again, let's see if we can see something more representative. Of course not, because that would be too simple. I don't know why the demo gods hate me today, but they do. Okay, well, normally you would see this take lots more steps, but you can see that we started out with a huge error, okay? We started out with a predicted model of 16.716 plus 14, a huge error. The weights less gradually than normally changed, and we wound up with where we needed to be. Okay, so let us see where we are. So basically just a few steps here, really, and we did some actual real machine learning. You saw we ran it multiple times. It kept coming up with the answer. So how do you put this to use? Okay. Main thing to remember here is you need to take small steps. You can't go from, black and white tintypes to VR in one step. You want to take little steps in between. And one great place to start is with analytics, because you are probably already doing some work there. You've already got the data, you've already got processes in place to determine what you're looking for and what to do once you find it, and you can get some real results. The most important thing is to know what it is you're trying to accomplish, because the best machine learning routine in the world isn't going to help you if you don't know what you want it to do. All right, and that's it. So we are ready for Q&A. So if you have not gotten your questions in, now is the time. Also, you don't forget that you can go ahead and grab that course. All right. So remember, if you're not viewing this live, click the link anyway, please. Hopefully we'll have something for you there as well. Okay. So what kind of questions do we have?
So not a lot, which is very surprising to me. And I can only imagine it's because of the sheer velocity that it's been going at. But while I'm asking the one we do have, maybe I've seen a few. Oh no, here we go. There are more coming in. I'll start with the first one. How do we account for the ways that machine learning determines how to do things, but into which we have no visibility? Given that machine learning has been documented to come up with surprisingly biased, even racist rules when learning how to do things, this would seem to be something we should address. So I guess it's like who polices the police kind of idea.
No, that's a really great question, and I agree 100% with that. It is a big issue. There is a terrific, I don't know if it's a book or a TED talk or whatever, but it's a terrific talk called "Weapons of Math Destruction," and I highly encourage you to go and look that up. We'll put it in with the notes afterwards. But it's very true, and I think it's really important that researchers and even people who are just working with the data are cognizant of this, because your data is very much going to affect whether you have these problems. I'll give you an example. If you have a machine learning routine that compares people who are applying for let's say for a promotion at a big company, and you've got a woman and you've got a man, and the machine learning routine compares these two candidates and decides that the man would be more successful. And the reason that it does that is because it has more examples of successful men, but it's not taking into account the fact that that's because it's been difficult for women to get into those positions in the first place. So this is something that humans are definitely going to have to really take in hand to make sure that we are keeping these things in check. I can't stress that enough. They're using machine learning now for sentencing in criminal cases, and it's exactly the same problem. So if you're looking for me to say, oh, that's not going to happen, I'm not going to do that, because it's happening. That's why we all need to understand this now. So that's my answer to that question.
That's excellent. Okay, we got one more opening up. Let's have a look. Oh, lots and lots of people asking to share the slides. We're not going to share the slides with your email addresses, because as you can probably figure out, that's going to be a real pain. So instead, what we're going to do is take the recording of this and put it online at that URL that I've just dropped into the chat. And next to it, we will attach a PDF of the slides. Now, it's not going to go up there immediately, so you'll need to check back. And that's that.
Right.
Okay. Yeah. Any more questions coming in? Answer live.
I can answer the optimizers question now.
Oh yeah, go for it.
So now that you know how gradient descent works, that you're trying to work your way down into that valley, there are different techniques that can be used. You can just take, steps that are always the same size. They have some techniques involve momentum. So like the steeper the hill, so to speak, the faster you go, which allows you to get past what are called these local minima, where it's not really the minimum, but it looks like it kind of where you are. There are techniques that let you kind of look forward. The problem with that is now you've got momentum. You might wind up overshooting the real minimum. They've got techniques that let you look ahead to see if there's a minimum coming up so that you can proactively kind of slow down, so to speak. So that's another thing. And that's kind of the difference between all of these optimizers, is which of these techniques they use for that kind of thing.
Cool, thank you. I see some people raising hands. I put a comment in the chat earlier. I can't give you the mic with a group of this size. So if you're raising your hand, please turn that into a question and stick it in the chat, and we'll make sure that it gets answered. All right, next questions. Let's have a look. I guess we can go to the top now with some questions from earlier. I guess you could choose yourself. There's 3 or 4 or 5 in there. We've got about 6 minutes left.
All right, so let's see here. How do you keep algorithms from increasing here's one. How do you keep algorithms from increasingly self-validating when anomalies might actually be beneficial to making your data set more accurate? There is a technique called cross-validation, where first off, there is a balance between relying too much on the anomalies and doing what's called overfitting, where you are too specifically trained on your training data and you don't generalize well, and underfitting, where you don't take enough of the details into consideration and you are not very accurate. And one way to kind of get a balance between those two things is to do what they call cross-validation, where normally what you do is might maybe take, let's say you have 100,000 data points. You might take 80,000 of them and train, and then test your routine to see how good it is on the other 20%. Another way to do that with cross-validation is maybe instead of just doing 80 and 20, maybe you'll do that 10, 20, 30, 50 times, but you'll take different 80-20 groupings each of those times. There's a lot of different techniques that allow you to do that kind of thing. Okay, so somebody asked.
There's actually another couple of questions coming in the chat now. Maybe we should jump to those. Adam Chandler asks, do you have a recommendation for which libraries or methods are best for unsupervised anomaly detection against log files?
This is a big question, actually. Somebody else was asking what kind of data is good for anomaly detection. This is a big thing, and I think what I'm going to do is I'm going to put together a blog post on anomaly detection, because I can't possibly answer it in 4 minutes.
Okay, that's fine. So we will share the slides. In there you can track down Nick, and from there you'll be able to find his further writing about this.
Yes.
So we've got 3 coming in on the Q&A, but there are also some in the sheet still.
Yeah, so let's see. How do you know what step size to use? Yeah, so there's a couple of ways that you can do that. Things like step size, and when you get into like neural networks, the size and shape of your neural network and all that stuff, those are called hyperparameters because they're parameters about your parameters. And there are different techniques that you can use to find the best hyperparameters. You could just guess, and you could do trial and error. You can do what they call a grid search, where you basically just run them all the different combinations and see which one is best. Obviously, that's not going to work well with a big problem. You can do random search, which lets you just sort of run a few and pick the best one, and then keep running more of the simulations, and while you're actually running your problem, see if you can find something better. So there are ways to kind of work on that problem. Let's see. I see someone is asking, does time-based databases common on the machine learning? I assume the question is actually, can you do machine learning with time-based databases? And the answer is yes. There is a technique called recurrent neural networks, which take into account things that happened in the past. That's the kind of thing you would use for like stock prediction and crypto pricing, but it's also the kind of thing that you would use for logs and so on, to detect patterns of things that are going on. Let's see, what do we got? We got 2 minutes left. When should we be using gradient descent? Anytime you have, you're trying to predict like a value, you are probably going to be using gradient descent at some point. Even within neural networks, typically behind the scenes, it's some form of gradient descent. Is that all there is? No, there are other techniques as well, but it's extremely common. So that's why I started with that, because you need to understand that. It's kind of the foundation of a lot of stuff.
All right, I think that's because we're coming to the top of the hour. I'm pretty sure at this point that people are trolling me with the hand raising, so I'm not going to mention it again. But that was absolutely fantastic. By far and away the busiest CNCF webinar we've ever had. I'm going to put the link in the chat once more. If you want to come back and get the slides or anything else later, or contact Nick, go there. Within about a week, both the video recording and the slides will be there. And then you can also get me on Twitter at Nick Chase. There we go. Nice, easy one. I'll drop that in there as well, at Nick Chase on Twitter. You can fire all your questions at him there. Thank you to everyone who attended and who was so active with asking questions. Nick, 1,000 thank yous for this. It was very informative. Thank you for having me. I really enjoyed it. And I hope everybody sticks around. And please go ahead and grab that book and give me your feedback. I would really appreciate it. There we go. Go grab the book, give some feedback. That's all we've got time for now. Thanks again, and bye-bye, everybody. All right. Thank you. Bye.